Hello everyone, I'm Jacqueline Lis from University Science Malaysia. Today, I would like to present my final year project with the title of Electrochemical Characterizations of Lithium Vanadium Oxide Anode with Agar binder in aqueous rechargeable lithium-ion batteries. So, what is aqueous rechargeable lithium-ion battery? It is a device containing electrolyte and electrode, and it operates based on the redox reactions. It is invented in 1994 and becoming promising system due to its high reliability. For high capacity rechargeable lithium-ion battery, binder play an important role to improve the battery performance. Binder is an gelling agent to bind all the components together. In our case, Agar was chosen as the binder instead of conventional binder. Thus, in my mind is, what is the problems faced by the binder now? The first problem is the conventional binder face safety, environmental, non-degradable and pricey issue. Second, the effect of the Agar binder ratio in LVO anode has not been a focus in previous research. Third, research focusing on the characterizations of LVO anode with Agar binder has seldom been done yet also. So this objective will create to overcome the problem. First, to prepare the anode for different Agar binder percentage to get the optimum ratio. Second, to determine the cyclic behavior, diffusion coefficients, electrochemical impedance and battery performance of the LVO anode. And last one, to characterize the degradation behavior of the LVO anode. To prepare the working electrode, LVO, graphene, and Agar binder in a wet ratio of 8:1 was measured. The wet percentage of the Agar binder for the anode varies from 0 to 20%, while the wet percentage of the graphene will fix as 15%. The measured powder materials will be grinded to achieve a homogeneous mixture, and in between, 1 drop of PTFE binder will be added to bind all the components together. The slurry will be formed into a circular shape before it was placed at the end of the stainless steel mass. Then it will be placed in an oven at 80 degrees Celsius overnight to remove excess binder. The dry slurry will be pressed through a hand pressing machine under 20 tons load pressure for 3 minutes and then dry again at 80 degrees Celsius for 2 hours to ensure the anode was completely dry. Finally, LVO anode was done by went through those process. After sample preparations, electrochemical characterizations such as EIS, CV, and CD were carried out in standard 3 electrode system. LVO as working electrode, platinum electrode as counter electrode, and standard chromium electrode as reference electrode. After electrochemical characterizations, the sample cut into 1 × 1 cm and sent for SEM, XRD, and EDX for failure analysis. It's result and discussion time. Cyclic voltammetry analysis will carry out first. From the CV curve, we can see that 8% Agar has the most prominent curve and it shows it has the fastest reactions among all. For 8% Agar electrode, 3 pairs of redox peaks were observed for the LVO working electrode. This is due to the intercalations and the intercalations of Li ion into or from the layer of the LVO structure. Besides, long-term CV can be used to determine the stability and degradation behavior of the anode influenced by the binder. The CV curve decreased upon cycling and the redox peak decreased from 3 peaks to 2 peaks. This might because of the loss of Li ion for the reactions result in no phase transformations at the third redox peak after 100 cycles. To further research the electrokinetics, the lithium diffusion coefficients of LVO electrode can be calculated by using Radial-Selvig equations. The diffusion coefficients of the Li ion in the LVO was calculated as 3.046 and 1.315 times to the power of -6. The anodic process is higher than cathodic. That indicates that the diffusion coefficients of lithium deinsertions is higher than that of the lithium insertions. Higher value of the diffusion coefficients means the ability of the lithium ion to diffuse in and out from the system. So, higher diffusion coefficients was more beneficial to the process. Study on impedance of lithium-ion battery is mainly attributed to anode impedance, especially charge transfer resistance. It is clear that from the table, the charge transfer resistance increased from 5.97 ohm to 6.91 ohm. Slowly increasing in charge transfer resistance in the cycling process indicate that the battery anode improve performance. That means the anode degrades slowly in the process. For the charge-discharge analysis, high initial capacity and discharge capacity can be seen from the table. The capacity also decreases as the cycle increases. That can be matched the result with the CV and EIS. In the previous work, charge capacity is 45 mAh per gram and discharge capacity is 70 mAh per gram in whole battery system. But in our case, only half cell system, so our reading is relatively high if compared to the previous work. According to journal, byproduct from the charge and discharging process will form on the anode, such as solid electrolyte interface. It competes with reversible lithium intercalations with promoting a large resistance at the interface. This is one of the reasons which leading to capacity fading. As we can see, the XRD pattern of electrodes are almost similar in 0, 50 and 100 cycle. The significant peak of the LVO anode, 100 in the lattice plane, seems to be disappear after cycling. The structural transformations of the vanadate is a main cause for capacity fading. Morphology structure of LVO anode indicate that the ability of agar binder play a vital role to maintain the cohesion of LVO particle. After 50 cycles, we can see some crack occur. A moderate contact loss and active metal deteriorations might lead to an efficiency decay of the electrode. But agar binder used to bind the LVO and graphene presented a significant result in this study. The result can be proved by EDX result also. From the EDX result, the weight percentage of the vanadate decreased from 0 cycle to 100 cycles. This is due to the dissolution of vanadium. Besides, fluoride became higher with longer cycle number. F formed on the surface was coming from the side reaction which from the PTFE binder. As a conclusion, agar binder showed that it could bind the active materials, current collector, and conductive material together after cycling. Moreover, it has a good battery performance in electrochemical characterizations, though the result might be subjective. But in overall, agar binder improved the lithium-ion battery performance. Therefore, I suggest that more research has to be done on agar binder to produce a better lithium-ion battery in the future. That's all from me. Thank you.